That's column 2, 1, 1, 2, 2.
1, 1,
Well, it's
2,
1,
and
1,
C
1,
2,
2.
2, 2, 2.
It was originally 1122.
What's that?
Originally it was 1122 before doing any kind of equation.
Yeah, I think the yeah. So this should be, sorry. This should be 2, 2, 2, 2, and this up here should be 2, 2, 2, 3, right? 2, 2, 2, 3. Is that right? I think that's right. I might have, yeah, I mean, the zeros are where they are, and if you just wrote those over,
This term.
what?
It's 1, 1, 22 in the original matrix.
Oh, yeah, okay, I see. Yeah. Yeah.
I think that is C221. That should be 0 because if C2223 is 0, then in the matrix you have written C22.
All right. How about this? If the original one was right,
Yeah.
put the zeros over it, and those are the components that remain. Right. I'll make sure and fix it in the notes that I publish before I publish them. Okay. Yeah. There's too many numbers to write down. Yeah. But the zeros, yeah, there's just use the zeros overlaying the original matrix, and that's right. But yeah, I'll fix it in the notes I publish. Okay. Don't worry, we won't write out all those equations anymore. But basically, we can carry these arguments forward. So if there are 3 orthogonal planes of symmetry, then additionally we have that C1 1 1 2 2 and C2 2 2 3 and C2 2 3 1 and C2 2 1 2. Those are all equal to 0. And so now you have 9 independent constants. This is called an orthotropic material. If there exists an axis about which a material has identical properties, then 5 independent constants This is called a transversely isotropic material. And so the reason I point this one out is, imagine you have a material like this that consists of several layers of material. So something like this. So some type of composite material that has microstructure like this, right? And so when we're in a continuum, we're not gonna model those three layers, right? Because let's say this is too small, you know, like this is a composite layer in an aircraft wing, right? And you want to do a simulation on the whole aircraft in flight, right? You know, like the Boeing 787 is made of composite, like it's a composite wing skin, right? So imagine this is like some composite layup of different materials, and you want to do a simulation of the wings in flight, right? Well, the fastest computer in the world is not going to allow you to have that kind of resolution where you can model each individual layer. So what you do is you homogenize it, right? You say, okay, this is one material, right? Looks like this, right? We're not going to explicitly model the individual components, right? But what we'll do to account for it is we'll give it different material properties in different directions. So in this case, in the plane, like if I pull on it in the plane, it's going to have one set of properties, and any rotation will give me the same set of properties, right? So if I rotate this in the plane and I keep pulling on it, I'll always get the same results, right? However, if I load it out of plane, then I get a different set of material properties, right? So in this case, this would be that transversely isotropic material, and I give this example in the terms of, you know, a composite or aircraft wing, but what do you think most sedimentary rocks look like, right? At some scale. They're going to be like this, right? They're going to have some, you know, transversely isotropic material behavior, right? So in the plane, you know, again, where we're homogenizing, right? We're not, you know, sometimes in our reservoir simulators, our grid blocks are on the orders of tens of meters, right? Sometimes kilometers, right? So, you know, sometimes our grid blocks are very large, but within that grid block, there could be like different sedimentary layers, right? And the deformation in the plane, no matter how I turn it, would probably be roughly the same material properties. But if I go out of plane, try to bend it, then I would get a different set of material properties. So a lot of engineering materials, you know, if they have any anisotropy, then a lot of times they look like this, transversely isotropic materials. Okay. Now let's go to the most common, or the most used.
Professor,
Yep.
what would be a vertical transfer of isotropic
A vertical transfer of isotropic? What do you mean?
in this direction?
Oh, well, it could be the same. You know, you basically would just rotate your initial axes, your initial coordinate axes. So you can rotate the components of, you know, so in that case we started with just like the XY plane being a plane of symmetry, but we could have chosen the XZ plane, right? Or the, you know, X1, X3 plane. And basically then our rotation matrix would have just been different. It would have been 1, -1, 1. And then the components that got zeroed out would be different, right? But we can basically you can rotate that. You know, if you had a different plane of symmetry, you could take the elastic constants that we wrote down and just rotate, or, you know, apply the rotation to the tensor, to the fourth order tensor, and they would rearrange the elastic constants in the way that they're supposed to be, right, for that plane of symmetry. Yeah. Or just formulate your problem, right? You can just rotate your reservoir, right, where it lines up with the X1, X2 plane, whatever.